Hi again, guys. Last lecture we were working with what? We were working with, yes, shear and moment diagrams. And I started the problem by using, let me show you here. Yes, we started this problem and we say this is an introductory problem for doing shear moment diagrams, and I'm gonna solve the first one by the method of the sections. So we say the first thing is the reactions, but we have to define some regions of interest, as I call them. Those are actually called discontinuity points. Those regions of interest are at the beginning and at the end of the beam. First, wherever you have a concentrated load or a concentrated moment, wherever the distributed load begins or ends, wherever you have intermediate supports, wherever you have a change in materials, wherever you have a change in cross-sectional area, wherever you have a change in internal supports. The points 4 or 5 here are applied basically for mechanics of materials, not for statics, because we assume that the whole section is homogeneous in the same material. But what if this part is aluminum and this part is steel? What if this part is 2 by 4 inches and this part is 4 by 4 inches? So what is from here to here? The section has a aluminum 2 by 4 and aluminum 4 by 4. Then I need to add something in between there. But in statics, don't worry about that. And then we did this problem by following the method of the section. Once you have those discontinuity areas, you just make a section, a start point, and then make a section, and then the point, and then make another section here. And we went and we did the shear and the first part, the shear, the second part, establish the equations, look for the values, and do the same thing with the moment, and that's it. That's what we did. So now, today, I'm going to solve the same problem, the very same problem, but I'm going to use the method of the integrals, so we can have a taste of that. Method of the integrals, shear and moment diagram. Method of the integrals, integrals and areas. I'm gonna solve the same problem by using both methods, integrals and areas. Same problem, same problem, same problem. This is the problem that I solved last time. This is 1.5 kilonewton per meter, 2 meters, 2 meters. And the first thing that you do is calculating the reactions, and we already did that in the last video, in the last topic, so I'm not gonna go through that again. This value was 2.25 kilonewton, the reaction at B, and the reaction at A was 0.75 kilonewton. That's basically, and then we say that point is A, that point is B, and this point here is called C. First thing first, same thing, line at the beginning, line at the end, and wherever you have a change, which in this case we demonstrated that it was only at this point, and we show why. Wherever the load begins, wherever the load ends, no concentrated load, no concentrated moment, nothing else. That's it. Horizontal line for the shear, which is going to be in kilonewton, horizontal lines for the moment, which is going to be in kilonewton meter. And we start. This baseline represents the 0, and everything that I'm going to plot above is going to be positive, everything that I'm going to plot below is going to be negative. Okay, let's start. What are we doing here? We are going to use the method of the integrals. Once I have the regions of interest, I start exactly in the same way that I started before. I start at the point A, and then I say, my God, there are people outside that are really loud. I'm gonna put a little bit of music because they are driving me crazy. Okay, good. If you don't like the music, sorry. Okay, so point A, and the question that you ask yourself, is there any concentrated force, because I'm doing shear first. Shear. Is there any concentrated force at that point? And the answer is yes. because I have a concentrated force coming from that reaction. So if that is the action, that is the value of the reaction, that is a concentrated force. What I told you is it's going to suffer a jump, the diagram, in the same direction of the force, in the same value of the force. So the first thing is that jump over there. Second, the next thing that we do is this. Now, span AC. And in span AC, I'm going to say that the shear is the integral of the load dx. Load that changes with x times dx. Now, this load refers to distributed load. Plus something that is going to come after I solve the integral. This something is not a constant actually, but let's call that boundary condition. And I'm going to explain you what is that. So the shear is the integral of the load. What is the value of the load here in AC? I'll give you 5 seconds. 5, 4, 3, 2, 1. Very good. You answered correctly. There's no load. 0. dx plus c. So this is going to be 0. And my shear is going to be constant. Now that constant is a boundary condition over there. What is that boundary condition? That boundary condition, if we are looking at shear and we are looking at the span AC, is the value of the shear at the point A, and this is read from the diagram. That's what you're gonna do. So in other words, you're gonna come to the diagram and you're gonna read the value at A. That's why it's important that you keep your diagram and you start doing your diagram and plot, calculate, plot, calculate, plot, calculate, plot. So the value is 0.75. So this value is 0.75. That means that this value is going to be 0.75 kilonewton. Now remember, this span AC goes from 0 to 2. That means that at 0, B is 0.75 kilonewton, and at 2 is 0.75 kilonewton because it doesn't depend on x at all. Now, if you check that with our previous, I mean, you should have it over there. I don't know where I have it. Here. You check that with our method of the sections. That's exactly what we got before. 0.75. That means that at the end it's going to be 0.75, a straight line. Oh, I love my drawings. 0.75. Imagine this is horizontal, please, and it's only one line over there. Use your imagination. So you go over there. Now the next thing that you do is what? You go to the point C, because remember, point, span, point. Now point C, is there any concentrated shear at C? And the answer is, check it. 5, 4, 3, 2, 1. Nope, there's not any concentrated shear there. Because there's not any concentrated shear here, we just continue and this value doesn't change. If I have a concentrated shear, remember that value should jump, but there is nothing else. Now we go to CD. CB. I don't know what happened with me all the time. D. B. Okay. My shear is the value, is the integral of the load plus C. Okay, this load is this load. And every time that I'm doing this and I'm explaining this to my students, they always, invariable, they tell me, what is the equation of this load? I ask them, and they say 1.5x. Really? 1.5x? You forgot your math. How that is gonna be 1.5x? And then I go and then I say, okay, let's do something. Because you don't know what is the equation of this. Let's change something for you. You don't know the equation for this. Let's do something different. I'm gonna call this y. and I'm gonna call this X, and I'm gonna put a horizontal line here, and I'm gonna say this value is 0.75, I mean 1.5, because that's the value of the load, 1.5. What is the equation of that line? Oh, the equation of that line is y equals 1.5. That's correct. Now let's make a dramatic change here. This is not y, this is w. What is the equation of w then? W equals 1.5. So what did you tell me in the first place? 1.5x. 1.5x should be that. 0 y-intercept x. This is not what we have, right? What we have is this. So my equation is 1.5. And this is what I have to put here. 1.5. So my shear is going to be the integral of 1.5 dx plus c. Now remember, what is c? C is the value. I'm going to keep writing this so you repeat it, and somehow that gets implanted in your brain. Value of shear at the beginning of the span, which in this case means C. And remember, you read that from diagram, shear diagram, it's obvious. So if you go to the shear diagram at C, you go over there and read that point. How much is that point? 0.75. 0.75. And now you just solve this and say V equals 1.5 integral of dx is x plus 0.75. I forgot something that you are going to forget. When you do the evaluation of the load here, and this is one of the important things, and this is one of the most common errors that students do all the time. Yes, the equation of this line is 1.5, but you have to add something little extra, which is really important, and you do only for the shear diagram. Because the direction of the loads is down, I have to put a negative sign here, and that negative sign goes only affecting the integral part, and this is gonna be negative 1.5x, and this is gonna be my equation for the shear. Remember, this negative sign is because these loads are pointing down. If these loads were pointing up, I wouldn't put this negative sign here. That is only applied at the shear. Copy that again. Because distributed load points down. And you can put a little drawing here in your notes that is pointing down. That's why you put this negative sign that affects only the integral part. Clear? Hope so. We're gonna see this later in other problems that I solve also. Okay, this is the equation. Once we have this equation, then you have to do the evaluation of the equation in CD. CD once again goes from 0 to 2. So for V at 0, then this is going to be negative 1.5 times 0 plus 0.75, and this is basically 0. No, yeah, and this is 0.75. And for x equals 2, V of 2, it will be negative 1.5 times 2 plus 0.75. This is negative 2.25 kilonewton of force, 2.25 negative. What is the equation of this? This is a straight line with y-intercept equals 0.75 and negative slope of 1.5. That means that we can come here now and draw my line, and this value should be negative 2.25. Now you go to this end. Once you go to this end, you look at your procedure, and your procedure is point, span, point, span, point. So you go, remember we were in CV, and now you go to the point B, and you say, is there any concentrated load shear? Yes? So that means that I find the reaction coming from my roller there. This value is 2.25. I have to have a jump at the point B from whatever is here, 2.25 up. What is the value that I have? Negative 2.25. How much I have to push it up? 2.25. How much I'm gonna reach at the end? 0. And remember, you're entitled to a small yes, because that means yes, I'm doing good. I'm so awesome. You can tap yourself. Okay, now we go to the moment. And we do the same thing. We're gonna go to the point A, and we're gonna say, do I have any concentrated moment at point A? No, because this is a pin, there's no concentrated moment, so I start from 0. Now you go to the span AC, and at the span AC, for the moment, you're going to say, okay, now the sound is bothering me. People, shut up, but you shut up also. Shut up. Good. Okay. Now, for AC, my moment, remember, is the integral of the shear plus a constant or a boundary condition. Remember, boundary condition value. Now, what is the moment? Well, the moment is going to be the integral of V. What is V? V is the equation of shear at AC. And if you go back, my equation of shear at AC is this one here, 0.75. So this is going to be 0.75 x dx plus C. What is C? Value of moment, because we are working with moments. Moment at the beginning, which means A. Read from the diagram. How much is the value of the moment read from the diagram? 0. That means that this value is 0. And my moment is going to be 0.75x. Oh, wait a second. What about the negative sign? No. I said that only applies to the shear, and I don't have to do anything in the moment. This is my equation. For x equals 0, moment at 0 is 0.75 times 0, which is 0. For x equal at the end of the span 2, here, moment at 2 is 0.75 times 2, which is 1.5 kilonewton meter. These are my values. So this value here is going to be 1.5 kilonewton meter, which I shouldn't even have to copy that. And this is the equation of what? Straight line. Straight line. Straight line. There you go. I'm proud of my line this time. There you go. Now, next step is going to the point C. Point, span, point. And then you ask yourself a question. Do I have any concentrated force at the point C? No. And I don't care, because this is not the question that I have to ask. I'm reading moments. So the question is there any concentrated moment at the point C? No. Keep going. Let's keep going now. Now I go to CB. Moment is the integral of the load, the shear, I'm sorry, plus C. What is the equation of the shear at that point? The equation of the shear at that point is this one, and that span. That's the equation of the shear. So that means that this is what I'm gonna put here. Moment is gonna be the integral of this, which is negative 1.5x plus 0.75 dx plus C. What is C? The value of moment at C from diagram. From diagram. Value of moment at C from diagram. What is the value of the moment at C from the diagram? This value here. What is that value? 1.5. That means 1.5. What about the negative sign for the moment? It was already included in the shear. We don't do anything else. Negative 1.5 x squared divided by 2 plus 0.75 x plus 1.5. That's the equation. If you want to simplify, you say moment equals negative 0.75 x squared plus 0.75 x plus 1.5. Oh, wait a second, I remember something. How weird. It's the same equation that we got in the problem that we did by the method of the section. You see that? It has to be different approach. Now we said for x equals 0, moment of 0 is negative 0.75 times 0, 0, 0, 1.5. And for x equals 2, why 2? Because 2 is at the end of the span. Who stole my sheet? At the end of the span 2 here. So x equal 2, moment of 2 has to be negative 0.75 times 2 squared plus 0.75 times 2 plus 1.5. Moment of 2 is, this is negative 3 plus 1.5 plus 1.5 equals 0. 0? Does that make any sense? So from here, 0. Of course it makes sense because this point is a roller. There's no concentrated moment here that pushes to 0. So the equation has to bring it to 0. Now I told you in the last video, in the previous video, that this was a very important point. And I told you also that the way this equation is going to go, it was going to go like this, and then it was going to come like that. And I know you are mathematicians, and I know you know this is a parabola because this is the equation of a parabola. But how the equation goes and how do you do that? Well, I know this point is going to be somewhere here, and you have to go over there and calculate that and see how much is that point, and I don't know. Well, how do you calculate this point? How do I know this is going to be a point here? How do I know if this is going to be a maximum, because this is a maximum here at that point? How do I know that? Well, because I'm me. No, I'm just kidding. So how do you do that? How can you calculate the maximum of a function? Well, you have to take the derivative of that and make the derivative 0 and look for the value of x that the derivative is 0. So let's take the derivative of that. What is the derivative of this? Negative 1.5, because this 2 multiplies by negative 0.75 x to the 2 minus 1, so x plus 0.75, derivative of x is that 0.75 and 0. That's it. The derivative of m with respect to x. So this is negative 1.5 x plus 0.75. That's the derivative of m with respect to x. And I have to make this 0. And when I make this 0, that derivative, then I have negative 1.5 x plus 0.75 equals 0. And then I pass this to the other side. So x equal 0.75 divided by negative 1.5, which is equals to 0.5. 0.5 meters. If I want to know what is the value of the moment, then I get this value that I calculated here, and I evaluate it at this point, and I say moment of 0.5, that's going to be equal to negative 0.75 times 0.5 squared plus 0.75 times 0.5 plus 1.5. And that value is, where is my calculator? Gosh. Calculator! Here. Negative 0.75 times 0.25. That value is 1.6875 kilonewton meter. That value is 1.6875. Let me see if I'm not mistaken. 1.6875. Now, my question for you is, why do I have to do all this process in order to find that value, and I have to take the moment and take the derivative of the moment, if in first place I got the moment by integrating the shear, and this is the equation that it was there. Remember that the integral of the shear is the moment, hence the derivative of the moment is the shear. I don't need to go again and do the derivative. I already have the derivative. So wherever the shear cuts 0, that's going to be either local maximum or local minimum moment. So the only thing that I have to do in order to calculate that value is going back and find my equation. Where is the equation? Here. My equation for the shear for that span. And say, oh, when this equation is 0, when the shear is 0, which is the same equation that I got again by deriving what I integrated. So you don't have to do that. I just did that to make you feel bad, and hopefully you did that. Now, how do you know the shape of the equation? Well, because you take the point of inflection points, take the second derivative if it's third degree, for example, because this is a parabola, but what if it's a cubic equation? I'm going to show you what you do old school. Old school, in order to know these shapes, you're going to use a circle, and that circle is that. That means positive decreasing, negative increasing, negative decreasing, and positive increasing. Easy. Positive, negative, decreasing, increasing. That's what it means. Now, what is important about the circle? This circle basically is a study of the slope of these things. So if you want to remember that circle, a student came with a mnemonic for that, and he said, please don't neglect infants. Please don't neglect infants. Neglect dumb people instead. Please don't neglect infants, neglect dumb people instead. So if you want to come with a new one and text me, not text me, by message me, it will be highly appreciated, because this is the only thing that comes closer. Now in Spanish I have a really nice one, because in Spanish this will be believe it or not, I'm translating from English to Spanish now, and that's my mother language. So this will be in Spanish, and I'm going to translate to Spanish. I'm going to convert to Spanish now. Not positive decreasing, but positivo decreciente, negativo creciente, negativo decreciente, positivo creciente. And in Spanish you will say, en español, you will say, por donde no conozco, no debo pasar corriendo. There you go, Hispanic people. Now you have another mnemonic in Spanish. Whatever, this is the way. And now, how I come with this shape? Well, in order for looking and knowing this shape, how this shape is going, if I'm looking at the moment, I have to look at the shear in order to know the shape of the moment. I look at the shear. Now, I'm going to look at this shape. This shape, here is easy because this is constant, that means this is a positive slope. In this case, this is positive. How do I know this is positive? Because it's plotted above the axis, maybe. This is 0, right? Everything that is plotted above is positive, everything that is plotted below is negative, so it's positive. Now it could be positive decreasing or increasing. Easy. If the area, or if the absolute value is decreasing, the absolute value is decreasing, is decreasing. If the absolute value is increasing, is increasing. So in this case, the absolute value of the function is decreasing. That means that it's positive decreasing. If it's positive decreasing and you look at the circle, positive decreasing corresponds with this shape. That shape is this shape. That's what I drew it like that. Now go to the other part. Positive or negative? Below, right? Negative. Duh. Now absolute value. What is happening with the absolute value of the function here? It's increasing. Negative, increasing. Negative, increasing is this shape, is this shape. There you go. Positive decreasing, negative increasing, and forget about now inflection points and all of those things. That works also with cubic, fairly good. I mean, this is just a graphic method, so you don't need to be that accurate. And that's the way. And once you reach 0 here, remember, yes, 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 amazing. Okay, good. Now I'm gonna go really quick and I'm gonna solve this problem. And when I say really quick, it's gonna be really quick. The same problem by the method of areas. It looks like a Dalmatian here. Method of areas. Shear and moment. Method of areas. Same value, same thing, same everything, same problem, same reaction. I'm not going to calculate it again, but this is the first thing that you do. You calculate your reactions. Same way of determining the interesting points or interesting regions or discontinuities. Same horizontal lines. And we start. Distances. Once you have your reactions, please pay attention. Don't even blink, because you're gonna lose information that can be relevant for the rest of your life. And then if you lose that information, it's gonna be a paradox in the time-space continuum. The fabric is gonna break, and I don't know, I'm tired. Okay, anyway, we're here. First thing first, point A. Point A. Is there any concentrated force? Shear, of course, because we're doing shear. The answer is yes. I have a concentrated force of 0.75 pointing up, 0.75 pointing up. Span AC. Do you see any force here? Any vertical force? No force. Constant. That means that this value is not changing from here to, oh, I went down. the chair came down. Okay, here, constant. That means that value is 0.75. Point C. You go to the point C. No concentrated force, no change. And now you go to CB. Now in CB, can you please remind me, what is the definition of integral? Yes, that's the definition of integral, the area under the curve. So we did the integral of this. Well, let's calculate the area of that. What is the area of this? The area of this is 1.5 times 2. That's the area of that. 1.5 times 2. Negative, because the arrows are pointing down. So that's a negative area. And I had a value before of 0.75. 0.75. So when I do this, this is going to be negative 3 plus 0.75 is negative 2.25 kilonewton. And this value here is going to be negative 2.25 kilonewton. And because this is constant, I know the integration of the constant is going to be a straight line. This is going to be like that. And now I go to the point B, and then I go to the point B, and I started the point B with the value of negative 2.25, but I find this force here of 2.25, that means that this is gonna end in 0, this is gonna jump to 0, I'm gonna go to 0, I'm gonna say yes. That's it. Shear diagram, done. Method of areas. Now let's go with the moment. That should work also. Moment. I'm gonna do moment here to save some trees. Moment. Point A. No concentrated moment. Starts from 0. It's a pin. It's a pin. You even can say it's a pin. Duh. Okay, anyway. No concentrated moment. Now, AC. What is the moment? The integral of the shear. Well, this is the area of the shear, because the integral is the area, and this is the shear. What is the area of that part? It's 0.75 times 2, which is 1.5, plus the value that I carried before, but the value that I carried before is 0, so it's 0.75. And I know this line is constant, so this is going to be a straight line, 1.5. Done. Now point C, no concentrated moment, no change. And now I go to CV. Well, you know something, I can't go to CV, because if I'm doing areas, I need to know this point. But I know how to get that point, even if I don't use integrals for that, or I can just use geometry for that. I can compare these two triangles that I have here, and I can say that 0.75, which is this, 0.75, and this is 2.25, and I know this distance is 2, and I know whichever of them is x. If this is x, this is 2 minus x, or let me call it differently, because to keep the same nomenclature that I had before, this is 2 minus x here. So then I can say that x is at 0.75, as 2 minus x is at 2.25, and I solve for x, and x is equal to 0.5. That's a way. There's an easier way, which implies basically, I'm gonna tell you guys, I feel in a good mood today. So instead of doing that thing, if you wanna know what is this point x here, and this is 2 minus x, and remember this distance is 2, you can basically just draw a parallel line to this one here, parallel line here to this one. So this is 0.75, this is gonna be 0.75 here, right? And this is 0.75, this is gonna be 0.75 here. So the total distance here, and this is gonna be also 0.75 here, because these two lines are parallel. So I can compare now this, which is 3, is up to this, which is 2, as this, which is 0.75, is at this, which is x. And then I solve x, and x is gonna be equal to 2 times 0.75 divided by 3, which is 0.5. This is geometry, simple geometry. Go back and review this if you want to. Whatever way you want to, you can calculate that value, and that value is 0.5. Once you know that value, same procedure, 1.5. Now you go to the span. What is the span? The span C prime? I don't know. So you start here and say CC prime. What is CC prime? CC prime is, I started with 1.5 positive, plus because this is a positive area. What is the height? 0.75. What is the base? 0.5 divided by 2, and when you do that, you have 1.5 plus 0.75 times 0.5 divided by 2. This is 1.875. 1.875. That means that this point here is going to be 1.875. This is a very important point. 1.6 0.6875. This is a very important point because it's going to give you the point of maximum moment, which is the point that is more stressed out, supposedly, right? And now you go to the circle again. Please don't neglect infants, neglect dumb people instead. And you say, okay, I want to know what shape is this, so I go to this one, positive, because it's positive, and the absolute value of the function is decreasing as I move to the right, positive decreasing, positive decreasing. There you go, this one here. And then I go to this point. I know it has to close in 0, no matter what, because this is a roller, and I don't have any concentrated moment, but I don't want to cheat. I mean, I could cheat, but I don't want to cheat. I'm giving you tips how to cheat. Because if I want to close it here, I don't have to do anything else. I say, what is this? Negative. Why? Because it's negative is plotted below, and the absolute value is growing, right? Negative increasing is this shape. I know it has to go here and come to 0. And I say, yes, I did it, I'm so awesome. And I cheated because I didn't calculate the value. Now, if you do that to me, I'm gonna know that you cheated because I'm gonna see it. I'm telling you how to do it, right? So don't do it, just work it out. I have this point for C prime B, and this point is 1.6875. I started with that point, and this is a negative area, so I have to subtract that area. What is that area? If this value is 0.5, this is 1.5 because the total is 2. 1.5 times the height, which is 2.25, divided by 2. And now, just to prove you that I'm not cheating, 1.6875 minus 1.5 times 2.25 divided by 2 equals 0. Yay! Now you can say yes. Done. So, summarizing, 3 methods we have used. Method of sections. Long, very good, very powerful. To me, long. There are people that love it. I don't love it that much. Method of integrals. Cool method. It works very good. Shorter than the method of the sections. But if you use the direct application of the method of the integrals, which is the method of the areas, it's going to be really fast and really good. However, there are some cases, and you will see later, that I will extremely advise you to combine methods, because some of the times when this area comes from a truncated triangle or a trapezoid, it's not that the method of the areas doesn't work. I'm just warning you. It always works, but it's much more difficult to calculate the area of that truncated triangle, the second area of that truncated triangle, because it's gonna convert like a triangle, like a parabola on top of a triangle, and that's not very easy to calculate. So in those cases, it's easier if at least that part you approach it by the method of the integrals. And I did some examples like that before. See you later, guys. Thank you for watching. I hope this helps you.